Welcome to Unit B for Science 30. This unit is on chemistry and the environment. And our first chapter begins with acid deposition. You may also know this as acid rain. So in this first lesson, we're going to look at the products of combustion reactions and then how they affect and cause acid rain. So by the end of this lesson, you should be able to outline the chemical reactions that produce air pollutants, and specifically sulfur dioxide, nitrous oxides, and also let's add in there carbon oxides or carbon dioxide, that when combined with water actually result in acid deposition or rain, and identify how human activities and natural events contribute to acid deposition in the environment. Now we're going to do that in this lesson, but we're also going to do that in future lessons. You can see also their textbook reference there, so if you would like to use your textbook as you're going through some of the examples, I'll be referring to the textbook. So combustion reactions, you've probably seen these before in grade 10 science, so this shouldn't be brand new to you, but it could have been a while for many of you. So one of the most common reactions in chemistry is the combustion reaction. And this is an exothermic process. If you remember, exothermic releases energy. So energy will be on the product side of your equation. Okay. And you can think about this because when you're having a fire, you're sitting around the fire, you feel the heat. So that reaction, that combustion reaction is producing energy. And we use this energy for a variety of different things. Now, in this example here, for this reaction, we have a hydrocarbon. And a hydrocarbon is something that's made of hydrogen and carbon. And that's all that's in that compound, hydrocarbon. For combustion to happen, it must have oxygen. Okay, so a combustion reaction involves oxygen and some kind of carbon-based biomass. And in this case, it is ethane. And we'll deal with how to actually name that in the second chapter of chemistry. So right now, this fuel is ethane, C2H6. So that means there's 2 carbons and 6 hydrogens in one molecule of this carbon compound. Now, whenever you have a combustion with a hydrocarbon reacting with oxygen, you always are going to have carbon dioxide and water released. So we're going to take a look at that reaction in a bit more detail too. So here's our combustion of methane this time. So here's our methane. It's carbon, 1 carbon with 4 hydrogens attached. This is the material that's being combusted or burned, is in way how we would talk about it with in regular every day. So we always talked about, we already mentioned that combustion has to have oxygen present. So you are going to get these products from this combustion when the carbon in the methane reacts with the oxygen. So carbon reacts with oxygen, that's where this carbon dioxide comes from. And then when the hydrogen in our hydrocarbon reacts with the oxygen, that's where the water, H2O, comes from. So whenever you have a combustion reaction with a hydrocarbon reacting with oxygen, you're always going to get carbon dioxide and hydrogen, as long as you have full, complete combustion. All right. So the next thing we're going to have to do, now that we know what combustion is, we are going to, well, after we do this, we're going to be doing some balancing of these formulas. Okay, before we jump to the balancing though, I just want to point out that cellular respiration looks a lot like combustion. It's basically the same reaction, but it's happening inside the cell. All right, organisms use this method, this cellular respiration, this reaction, to take that sugar that they've received through the blood into the cells, and then turn it into a molecule which is called ATP, and this molecule holds all their energy. Okay, so this is basically their energy power and energy compound in the cell. So we do cellular respiration. You've got glucose, or your sugar, reacting with oxygen. This reaction, again, it's exothermic, just like combustion. And you produce carbon dioxide and water, exactly the same as combustion. It's its form of combustion. And you'll look You have a hydrocarbon here. In this case, it's glucose, has an oxygen in it as well. All right, reacting with oxygen, producing carbon dioxide and water, just like combustion reaction. And it's exothermic. Exothermic. Now, this reaction is happening in the body. So we know what the body temperature is, around 38, something like that, 37 degrees Celsius. So this water here is in liquid form. All right. Whereas when we're burning a fire, I can't go back. When I'm burning a fire, and we're doing a combustion reaction, really high temperatures, so that water in a regular combustion reaction is going to be a gas. It's going to be in the gas form. So you would see a little G like that. All right, so one of the things you do need to be able to do in this lesson is balance a combustion reaction. And it's nice because when you're balancing these reactions, there's kind of like a little step-by-step you want to follow. You always want to do this order, otherwise it can get really messy and confusing. So just a couple things before we start balancing this, just to remind you, say you have a compound, say you have a carbon dioxide molecule. In that molecule, you have one carbon. So you'll see there's no subscript beside the carbon there. But if you were to put one, it would be a little 1. But we never put ones in, so we take that away. But basically, there's one carbon in that molecule. And then this 2 tells you that there are 2 oxygens. Now, if I took that same molecule of carbon dioxide and I put a 3 in front of it, that means everything after has to be multiplied by 3. Okay, it's not adding, which sometimes is what people get confused. You're going to be multiplying. So you have 3, however many carbons you have, and 3 times how many oxygens you have. So because we only had 1 carbon to begin with, if we go 3 times the 1 carbon, so we now have 3 carbons. And then 3 times this little subscript 2 tells us we have 6 oxygens. Okay, just wanted to make sure that that's clear and that you're not adding that 3, that prefix number. Coefficient. Thank you. All right, so when we're balancing this reaction down below, now this is an example in your textbook. If you want to walk through the example, you can. It goes a little slower. We're going to start with carbon. So we're going to balance carbon first. So we're going to look on our reactant side. So that's before the arrow. And we want all the carbons on one side to equal the carbons on the other. Right now, the only carbon I see is this C2. So that tells me I have 2 carbons on this side. On the other side, the only place carbon shows up is in carbon dioxide, and there's just 1. And there's no number in front of carbon dioxide, so we just have 1 carbon. So we're going to take whatever side has the least number of carbons, and that's the side we are going to make equal to the other side. So we need 2 carbons, so 2 times 1 would give us 2 carbons. So if we put a 2 in front of carbon dioxide, that now multiplies by the number of carbons. So now we have 2 carbons here, and we have 2 carbons here. So they're balanced. Done carbons. So let's take a look at hydrogen atoms now. On our reactant side, we have 6 hydrogens. On our product side, we have 2 hydrogens. So to change that 2 so that we have 6, we're going to multiply this side by 3. So we want to multiply the hydrogens by 3. The only place that we can add numbers is on these lines in front of our molecules. We can't add little subscripts and change the compounds or anything like that. So now we go 3 times 2, that's 6. So we have 6 hydrogens. And now we have 6 hydrogens, so we're balanced now. Last thing you always want to do is check the oxygens. Alrighty, so let's check our oxygens. So on our reaction side, we have 2. Over on our products now, this is where you want to be careful. We have 2 from the carbon dioxide and 1 from the water. So we have 3 oxygens on that side and 2 oxygens over here. That's tricky. All right. Except, wait, I've just messed this up. We need to go and look at our equation that we've actually been balancing. We can't go back to the original one because we've been putting in our numbers. Okay, so let's start again here. So our reactant side, we have 2 oxygens right now. And on our product side, we have to be careful because we've put a 3 in front of water. Water normally has 1 oxygen, but because we have 3 waters, so we now have 3 oxygens here. And now let's look at our carbon dioxide. Our carbon dioxide normally has 2 oxygens, but we've put a 2 in front of our carbon dioxide. So 2 times 2 gives us 4 oxygens. All right, so in total, we now have 7 oxygens. All right, now, if we want to have 7 oxygens here and we have 2, what are we going to do? Well, say it was 6 oxygen. It's probably really easy to figure that out, right? If you had 6 oxygen and you had a 2 oxygen here, you would put a 3, right? So 3 times 2 would give you the 6. But because we have 7, which is an odd number, what we write is a fraction. 7 over 2, basically, which is 3.5, right? 3.5 times 2 gives you 7 oxygens. So we now have 7 oxygens. Now, if you don't like working with fractions, one thing you can do, the next step, would be you could multiply all those coefficients by 2, and you would then have 2 C2H6. So there was a 1 there, but you multiplied it by 2, plus 7 over 2 times 2 is just 7. And then you have 2 times 2, which is 4 carbon dioxides, and 6 waters. All right, so dealing with the fractions is probably the hardest kind of balancing you're going to have to deal with. Just a couple things to point out. Watch when oxygen is the hardest one to balance, and watch, usually it'll appear in 2 different molecules, so watch that. Oxygen shows up in water and carbon dioxide, so make sure you're adding them both up. I strongly suggest going through this example in the textbook. I also strongly suggest watching this video that's on the next slide. There's a few more balancing combustion reactions, example questions here, which will really help you out. Make sure you do those practice questions right away so that you know if you can do these. All right. All right, so the carbon cycle. So besides cellular respiration, there's many natural processes that contribute to the carbon cycle. So not only is there animal respiration that adds carbon dioxide to our atmosphere, but we also have forest fires, volcano eruptions, certain rocks, when they get weathered, they release carbon dioxide as well. However, what we're seeing is that humans have a major impact on carbon being released in our atmosphere. And this would be due to factory emissions, vehicle emissions, also increased numbers of cattle, yeah. So we're going to look at how that affects not only the carbon cycle, but our environment in general. So we also need to just take a quick look at what incomplete combustion is. So we've looked at complete combustion up until this point. When we have complete combustion, we get carbon dioxide. When we have incomplete, that means there's not enough oxygen present. Okay, there's not enough. Or there is something causing this reaction to be not very efficient. So instead of carbon dioxide being formed, we're getting carbon monoxide. And this is the product of incomplete combustion, and it is a poisonous compound to humans. So let's take a look at these oxides of carbon. So when we have combustion reactions, we will have either complete combustion that forms carbon dioxide, or we'll have incomplete combustion that forms carbon monoxide. And you might even have a reaction of complete and incomplete combustion happening at the same time. So you're getting carbon dioxide and carbon monoxide being produced. Now, what are the differences between these two carbon oxides that are being produced? Well, we just mentioned carbon monoxide. It's a threat to human health. It actually blocks oxygen's ability to bind with hemoglobin, right? And we learned about that in the last unit. And this will affect the amount of oxygen that's available to the body cells and can actually result in our death. So this is why it's highly recommended that all houses have carbon monoxide detectors, because you can't actually smell carbon monoxide. So if carbon monoxide is being produced, you'll have no way of knowing until it's too late. So carbon monoxide detectors are invaluable in the home. So just check and make sure you have one in your home. And if not, definitely a worthwhile investment. So carbon dioxide, this is from our complete combustion reaction. Now, you may have heard this term before back in Science 10 or other courses. It is considered a greenhouse gas. That means when it enters the air, it helps goes into the atmosphere and helps trap the heat into our Earth, causing the temperatures on Earth to increase. Now, we're going to look more at that in our last unit. But let's just keep in mind that CO2 is a greenhouse gas. Now, it also can go up into the atmosphere and react with water, because there's water in our atmosphere, right? It's hanging out in the clouds. So when it goes up in the atmosphere and reacts with water, it forms carbonic acid. And there's a reaction down below here. Hopefully you can see it. Carbon dioxide going into the atmosphere with water, forming carbonic acid. Now, in the atmosphere, if you're creating acid like this, that is getting into the water that's up there, and this is causing acid deposition or acid rain. So when the precipitation falls, this carbonic acid is in that precipitation. So this is a good video. I strongly suggest you watch these videos. I don't put very many in, but this is a good one. It talks about what combustion is, complete versus incomplete, the two products, and then the effects of these combustion products. Okay, moving on to some other oxides that cause acid deposition. And both of the oxides that we're about to see are caused when we, one of the ways that they are created is during when fossil fuels are being burned. Okay, so in our atmosphere, normally, nitrogen is actually the largest component of the air we breathe, and yet we don't use it. So it makes up 80% of the air that we breathe. So when we have fossil fuels burning, like in our car or something like that, it's going to draw in the outside air and use the oxygen for combustion, but also nitrogen's getting in there. And nitrogen at really high temperatures will actually react with the oxygen. Okay, and it forms nitrogen oxide. All right, now this nitrogen oxide can then react with oxygen in the air to form nitrogen dioxide. And here, nitrogen dioxide, here we go. So we got nitrogen burning or combustion with oxygen gives us nitrogen monoxide. And then the monoxide reacts with oxygen to form nitrogen dioxide. All right, now nitrous oxides can lead to smog, which we're going to talk about. This is a really heavy pollution in the air. When you look out and you see that like kind of orangey haze over a city, that's smog. It also acts as a greenhouse gas. Like I said, it traps in the heat to our Earth, but we're going to take a look at that one later in the next 2 units away, actually. And then it also reacts with water in the atmosphere to form nitric acid. Look, another acid it forms, okay, which causes another cause of acid rain. So we're getting all these, we're burning things, and these are releasing all these oxides into the air that react with the water, like the precipitation, the snow, the rain, and then falls as acid. So the other oxide that we need to look at is sulfur dioxide or sulfur trioxide. Sulfur gets in the atmosphere when we burn coal to produce electricity. Or if you're flaring a sour gas well, then that hydrogen sulfide that's in there reacts with the oxygen to form sulfur dioxide. Um, so sour gas is natural gas that contains a larger amount of hydrogen sulfide, or you might know it as hydrosulfuric acid, and it's toxic to humans. And so this has to be removed, and it's in a process called sweetening. All right. Now, if you release these different oxides, these sulfur oxides, into the atmosphere, you can have sulfur dioxide reacting with oxygen to form sulfur trioxide. So there's 3 oxygens there. This sulfur dioxide can also react with the water that's in the atmosphere already and form sulfurous acid. And the sulfur trioxide can form sulfuric acid. Both of these acids here will form acid rain or acid deposition when they go up into the atmosphere and react with water. But they're in the atmosphere. When they come down in the rain, they are acid rain. Okay, so it's a little bit about where's our oil coming from, and how does this relate to what we were just talking about. So where are those oil sands? Well, the oil sands are up here. Let's take a look at the oil that we're getting from that sands. This is like oil it's mixed with like sand and clay, water, bitumen. It's really heavy. Look at how they're holding like the oil sands right there. It's really sticky, viscous. It has to be refined quite a bit, so that we can turn it into the products like gasoline and diesel that we can use in our vehicles and other areas. Yeah, and so um, there's also a lot of sulfur in these oil sands. And before we start burning any of these fuels, we need to get that sulfur out. So there's quite a process, and it leads to a lot of sulfur being created. And there's these really amazing pyramids, the Great Pyramids of Alberta, that are being built right now in the Athabasca oil sands. This is at the Syncrude oil processing plant, where they're taking out sulfur, and these piles here are sulfur. And if you look at the base footprint of these pyramids, they're actually 4 times bigger at the base than the Great Pyramids of Giza in Egypt. So when these pyramids are done, they're going to be way bigger. So right now, so you can see there's the pyramid like in Egypt, and here they're just starting to build the pyramids. But you can only imagine how much larger that pyramid is going to be. Pretty fascinating. So that's sulfur that's been taken out of the oil sands and out of the fuel sources that we're going to be using, so that we don't burn that sulfur and release it into the atmosphere and cause more acid rain. So there's a great video here on acid deposition, acid rain. Take a look through that. All right, so sulfur dioxide, we did talk already about some of the sources of these. There is a good data booklet in there's a good chart in your textbook where you can see some of the human-made sources and some of the natural sources of these different oxides. Make sure you know those. And also these diagrams of or maps of Canada that show where the sulfur dioxide and nitrogen oxides are being released, and you can see they occur mostly where there's Canadian centers like big cities. So there's coming from our exhaust pipes, but also from some refinery processes too, you can see. And all in all, like, emissions are a way we talk about everything that comes out of that tailpipe, basically, any of those byproducts from our combustion reactions. So we've talked about the different oxides like carbon dioxide, sulfur dioxide, nitrogen oxide that could come out of there, but there's also particulate matter, and these are very, very small particles like that. So look at the size of like sand versus a hair diameter. It's very small, this particulate matter. And these particulate matter can lead to asthma and other respiratory diseases because these particles, we breathe them in and they actually get stuck in our lungs too. And then we can have reactions to them and that can cause asthma. Also, these emissions, especially if you have incomplete combustion, a lot of these particles that are coming out are considered carcinogens. And remember that word from last chapter. Carcinogens are cancer causing, or because they cause mutations in our DNA, like we talked about in the last unit. All right, so that's a quick run through of this lesson. Obviously, go back, review the slides, read your textbook, try your practice questions, and we'll see you in the next lesson.